In this video, we are going to learn why, if the curl is 0, our vector field is conservative. So let's recall that previously we've said that if the curl of a vector field is 0, then our vector field is what's called path independent. Path independent. And that's equivalent to saying that our vector field is conservative. So what does path independent mean again? It means that if I have a path that starts at a point A and ends at a point B, then if I take some path that starts at A and ends at B, so maybe I'll call this path C1, and I'll draw a direction arrow, and I take some other path that starts at A and then ends at B, maybe I'll call this path C2, that the work done along either path should be the same. It only depends on where it starts and where it ends. And the work is given to us by this line integral of our vector field. So now we are in a position to show why. Okay, so let's give a mathematical reason for this. One of the things I want to notice is if I were to take this curve that travels along C1 and then I sort of go in the opposite direction of C2, it's a closed curve. And I'm going to call that new curve C. So C is going to consist of C1 union the negative of C2, which means the opposite of C2. So this is a closed curve. A closed curve. So let's consider the line integral over C, this closed curve. Let me put it in pink, just because I've been putting it in pink. And then it's a closed curve, so I'll put a circle through my integral of my vector field dot dr. So because this is a closed curve, we can use Stokes' theorem. We can use Stokes' theorem here. Because what Stokes' theorem says is this will become a surface integral over a surface S that has this curve C as its boundary curve. So I might imagine S as some surface here that has this curve as its boundary. And these points could be in our 2D XY plane, they could be in three-dimensional space. So this surface could very well be some curved surface. And then within that surface integral, we take the curl of f dotted with the unit normal vector ds. It turns out the surface itself doesn't really matter because we're assuming that the curl of f is 0. And if the curl of f is 0, that's the 0 vector, when you dot it, that's going to be 0. And then doing the surface integral of 0, well, that's going to give us 0. So the right-hand side is 0. So the left-hand side, I'm going to split up this integral over my closed curve into two pieces. So I'll do the line integral over that first piece, C1, of my vector field dot dr, and then plus the line integral over the second part. But the second part, we're going in the opposite direction of C2, and we are calling that negative C2. Negative C2 of my vector field dot dr. Okay, so the first integral stays as it is over C1 f dot dr. But what I want to notice is when we're traveling along this curve negative C2, that means in this direction, that's going to be the opposite of the work that I would get if I traveled along the forward direction of C2. So the way that I write that is I have to switch the sign of the integral as a minus, and then integral over now the forward direction, just C2, f dot dr. F dot dr, and that equals 0. And now, because I have this negative integral, I can move that to the other side to make it positive. And that gives me the line integral over C1 of f dot dr. Well, that's going to be equal to this line integral over C2 of f dot dr. In other words, the work done by the vector field along this path C1 equals the work done by the vector field on the particle along the path C2. So, and the path C1 and C2 are arbitrary, which means no matter what path I took, as long as it started at A and ended at B, we get the same work. So our vector field is path independent. So that is a mathematical argument for why, if the curl is 0, then our vector field should be path independent. So there are some details that I'm omitting, like there's some conditions that we need about our region, but in most cases, and certainly in the cases we're going to consider in our class, this argument holds. So I want to end by giving just a brief, kind of more conceptual explanation of like, why is this? Like, this is just a math argument, but what's the conceptual sort of visual reason for why if the curl is 0, then our vector field is path independent? So remember that the term curl is sort of telling us, like at a point, how much our fluid would sort of rotate around that point, whether it's counterclockwise or clockwise. So it's sort of telling us a measure of like the swirling of our vector field. Maybe if our vector field is a velocity vector field describing the movement of some fluid. And path independence. So path independence would be sort of telling us that the work done by this vector field on some particle that's moving along some path doesn't depend on the path. It just depends on the starting point and the ending point. And one of the examples that we have of a path-independent vector field is gravity. And I could think of a situation where like we're climbing up a hill, and whether it's like a very steep hill and I start like down here and I end up here, or I have a very gradual hill, if I start at the same altitude and I end at the same altitude in the two situations, the work done here versus the work done here would be the same. So it just depends on the starting and the ending point. In other words, it's kind of based on the work is sort of telling me the change in my potential energy. And in the context of something like this, like where I have a fluid moving around, well, the curl is kind of describing whether there are these sort of rotational tendencies, there's rotational forces. And if the curl is 0 everywhere, no matter what point I took along the curve, there aren't any rotational sort of tendencies around it. So that's never going to either add energy or lose energy as we move along the path. So all that's determining that sort of like change in potential energy is where we start and where we end. And that's going to be the same no matter what path I take along it. And that's a more conceptual reason for why this is. So in terms of our goals for this section, we've now learned what Stokes' theorem is, how we can use it to more quickly compute integrals, whether it's a line integral over some boundary curve or a surface integral that has this form, the curl of f dotted with that unit normal vector.